you very much. It's exciting. Yeah, it's my first talk in person as well. Right, so this was going to be a talk about a subset of modified gravity theories and UV completion and what happens when you try to UV complete them. So in case some of you don't know, to UV complete a theory means to generalize it to higher energies. So you've got some theory, maybe it stops working at some point, everything breaks down, your predictions are worthless. But if you can generalize it to something more fundamental that survives at the higher energies, then you have your UV completion. Some people take this to mean that it's valid at all scales. Some people just take it to mean that it's valid at higher energy scales. So this is usually what most people use the term with. Okay. So some more background. So it's a general feature of any theory that attempts to solve the cosmological problem and essentially try to explain why it has such a ridiculous value to come with extra degrees of freedom. The simplest of which is one extra scalar field. The point is, the moment you bring in one extra particle, you have also brought in a force mediator. You can't have one without the other. You bring in the extra particle, that particle mediates also some kind of interaction. And so you find yourself with an extra fifth fundamental force, in addition to the one that we know and love. So at slide 1, you can already ask yourself a question. Do we see any extra forces? Because if we have a fifth one, do we see it? The first answer you can give is a resounding no. So what I'm showing here is what happens when you allow for one extra potential. So in addition to the gravitational potential, you add one more force that has a finite range due to the fact that the scalar field has a mass. So when you've got a massive mediator of force, the range is no longer infinite, it becomes finite, and the more massive the field, the smaller the range. This is the way it works. So what I'm introducing here is this extra potential where the range of the fifth force is determined by this lambda that's related to the mass, and then you've got the strength of this fifth force that's also regulated by this alpha that gives you the coupling. And what these two plots show, they are both exclusion plots, and they show you the exclusion region that comes from solar system experiment and Earth-based experiments. And so this is not even up to date with now, but essentially it's more and more excluding. So as far as we can see, no evidence of these extra forces from either Earth-bound and solar system-bound experiments. So this is slide 2, and my talk, has it finished at slide 2? Actually, no. I mean, I'm not here for nothing. It turns out what this is really excluding is just the simplest possible model. So what this means is really that it's a canonical scalar field with a small mass that's disfavored. So for those who speak Lagrangians, this is the Lagrangian. For those who don't, all you need to know is this is just the simplest possible model. So you may wonder, well, what's wrong with the simplest possible model? Well, this is a linear model, just a linear model. To give you an idea, the Higgs boson, which is the one scalar field that we know that exists, doesn't behave this way. So the Higgs boson can't be used for dark energy, but to give you an idea, one of the reasons why this is not sufficient, this doesn't end the story, is that the one scalar field that we know that exists doesn't just do this. So it's worth to consider more complicated models. And in fact, it turns out that if your scalar field has non-trivial self-interactions, then your fifth force may display an interesting behavior. It may display screening, which means that your fifth force becomes dependent on the environment, and in some regimes, it can be suppressed, okay? This is useful because then you have an explanation as to why you don't see it in those environments where it has to be small in order to make sense with the observations and the experiments we have, but you can still have it to be useful for cosmology. Now, I can already sense some of the observers between us saying, this is a cheat by the theorists to evade my latest constraints. No, it's not just that. Actually, I will show you in a moment that even at least one of the theories that we know that exist, electromagnetism, shows screening. But before that, in terms of the solar system experiments that I showed you earlier on, the reason why this would work is that you're making several quantities background dependent. So maybe it's the coupling that depends on the environment. Maybe it's the range of your field force that's not equal everywhere. So maybe it's the mass of the scalar field that depends on where it's sitting. So in some environments, it's like its effective mass is bigger, and in other it's smaller, and so the range of the force can change. Or maybe instead of being sourced by an entire mass, it's only sourced by some part of it. So this is the case in actually in several models of screening, where all that matters is just a shell around the source radius. It's not all the mass that matters, but just some fraction of it. Okay. And this is what I was saying about, it's not just a cheat. So this is something that electromagnetism kind of displays as well. Let's take an example when you've got a charged plasma of charged particles, and you've got one electron going through it. It turns out the influence of a charged particle is only felt up to a Debye length, which can be phrased in terms of a Debye mass, where the Debye mass will be a function of several things, including the electron density and the temperature of the plasma. Now, the point is you can phrase this situation as if the photon, which is the mediator of electromagnetism, it's as if the photon has acquired a mass within this charged environment, and so electromagnetism has become finite range. So this is not completely crazy, okay? So this is something that can exist, and this is called the Debye screening of electromagnetism, okay? So it's not completely ridiculous as an idea. Right, and in fact, and I'll be honest with you, one of the reasons why I briefly talk about chameleon screening is because it gives me a chance to show a picture of a chameleon, which is such an amazing creature. Why would you not do that? What I've just showed about the Debye screening of electromagnetism is similar to chameleon screening in modified gravity. So in this case, you've got this extra scalar field, and in the environment where you've got a high density, like towards the center of a galaxy, then the chameleon mimics the environment. So high density becomes big mass, and so the range of the force is small. And towards the outskirts of the galaxy, where the environment density is small, then the chameleon mass also becomes small, and so the field force becomes longer range. And so then it can play a role. So then it can have an effect. So it's typically in voids that you see more of this. So this is just one example of how this can be achieved. Okay, so before I go on, questions already?
No questions.
Yeah.
Should we dim the lights a little bit? Because you've got some really nice pictures. We don't have to, not all the way.
Okay, thank you. And by the way, remote people, can you hear?
All good.
Thank you. Okay, so in this talk, I'm going to focus on a different type of screening mechanism. It's called the Vainshtein screening. So in this case, it's as if your field force behaves according to two different laws, depending on the environment. So in order to show you how this is possible, I'm showing you the equation of motion for the cubic Galileons, which is the simplest model showing Vainshtein screening. And on top, you can see standard gravity. So the difference is in these terms here, which in my intention would be aquamarine, but I'm not sure you can see that. So imagine they are a different color, okay? Now, closer to a compact source in this theory, you have that these non-standard terms dominate. These high derivative non-standard terms dominate. But far away from the source, you get that again, just the standard terms. So this box term and this source term matter again, okay? So closer to your massive source, you've got these terms, and further away, you've got these other terms, which means that...
Sorry, can I stop you there? What do you mean by standard gravity there? The phi is the Newtonian potential?
Yeah, but Newtonian
okay.
potential. Yeah, sorry, yeah, Newtonian.
And so the other terms are also working on the Newtonian potential, but they are non-linear.
Yes.
Is that it? Okay.
Yes. And basically, you can have two approximating regimes.
Okay,
one in which you can ignore the big important part comes from this term, and one in which the standard terms dominate again. So you can show that that I've got a different way. Okay. in terms, in more comprehensible terms, you can show, because that particular example can be integrated and you can have an analytical answer to this, you can see that closer to your massive source, your scalar force is behaves, basically scales like radius to the 2/3, so it's weaker than gravity, but further away from the source, you recover the 1/r² behavior. And so it's got a strength like that of standard gravity. And this transition happens around a so-called Vainshtein radius, where the catch is that it's huge compared to the size of the source. So to give an idea, even if basically the Vainshtein radius by which we would be screened would be something like the size of the galaxy for us, okay? So incidentally, while you can make some lab tests of screening for other models, in this case, you can't because you're screened even by the galaxy, okay? So this is the problem. It's also one of the reasons why this particular screening mechanism is more difficult to test compared to others. It's quite efficient. Okay, so it's like you've got two different force laws depending on what they are. And this is given by these quite horrible, complicated, high derivative nonlinear terms, okay? Right, this is where we already get into the problem. Before I go into the problem, questions, clear? I'm going to ask this a lot, just get used to it. Right, yeah.
How does the time part of those derivatives work? Does
Oh.
it apply for that highly dynamic fields or something as well?
Yeah, that's a very interesting question. So the current answer obtained with linearized equation is that the time dependence of Einstein screening is completely unscreened. So if you've got a theory with does this answer your question, by the way? Is this what you want?
Maybe,
Yeah.
I think so.
Yeah, so the idea is that if you've got a time-dependent system with a theory that has Weinstein screening, then it's unscreened, and so you get to see the extra fundamental force. It's not screened because the time dependence of it is not screened. You can really tell it apart from standard Newtonian gravity. So this is the current answer. The reason why I say current answer is that presumably you can dot the i's and cross the t's a bit more, but the basic picture is likely to be correct. Yeah.
Follow-up question. So for something like the Hall-Taylor pulsar, which is a time-dependent system, but is sitting inside a galaxy, so is it screened or not screened?
I think the standard answer is that it's unscreened. And I think, to be honest with you, I think the broad picture is likely to be correct. It's just that this has been derived using linearized equations. So I think the broad picture is going to be correct, most likely. I just think what can happen is that you probably need to dot the i's and cross the t's using the exact equation of motion, and you can just derive slightly more accurate constraints. So I don't think the basic picture is going to change, but presumably you can make it a bit more accurate. I think the inverse case is more interesting. So for instance, the idea is that instead with Chameleon-like screening, the idea is that that is screened, the time dependence. Now, if you were to dot the i's, cross the t's, and find that there is even just a little unscreening in that, then maybe you can make a new test. So in that case, I think it's more interesting. So this has been done with linearized equations. So as I said, it's not like it's wrong. It's just that if you're lucky, maybe you do the test with the full equation of motion, and maybe you find that there is even just a leak of time dependence in the Chameleon-like screening that's not completely screened, and then maybe you can make a test of screening with it. In the case of Einstein screening, what can happen is that maybe it's a little more screened than we think, but still likely to be mostly unscreened.
Okay, so if the broad picture is correct and there isn't some kind of reshuffle effect, then the Hall-Taylor pulsar, for example, because it's super well measured, would rule out Weinstein screening?
Yeah, Weinstein screening. Okay, so I should add something else. Another problem, which incidentally is actually related to what I will be talking about, is that this theory with Weinstein screening have a limit of validity that's actually quite poor. So one of the troubles with those systems is that it's unclear that you can make any computation at those scales using these theories because they break down. So this is this is one of the reasons why those constraints, it's unclear that you can actually take them as they are, because it's quite possible that the theory has broken down or it's not working well enough. In that range. So I think So it was actually a really good paper, that one that calculated the effects, the so-called piercing of the Weinstein screening, I think it was called. Yeah, that was a great paper. So that's one aspect. I think maybe you can, as I said, dot the i's and put in the full equation of motion. The other aspect is, can you actually trust these theories at the scales that would be relevant for those systems? That is unclear.
Okay.
That is unclear. Yeah. And in fact, this relates to the argument that I'm going to bring up now. There is a problem with what we've been saying about these different regimes because, as I was saying, these theories have a limit of validity that's much smaller compared to general relativity. Normally, people say this is not a problem because you don't need this theory of gravity to be the actual theory of gravity. You just need it to be some suitable limit of a more fundamental theory, but you just need this limit to apply. But the problem is that by doing this, they are putting themselves in a perturbative regime. So the idea is you've got some unknown, more fundamental theory. You are restricting this more fundamental theory to some scales you're interested in, and you're essentially saying that everything else is perturbative. It's like when you do perturbation theory on the density field, for instance, or on the density contrast, and you say, okay, so I'm in a perturbative regime, the second order is small compared to the first order, and so on. Now, if the perturbative approach is correct, if it holds, it's all good. But do you know that it holds? Because you're simultaneously saying, I've got some regimes where the non-standard terms are dominant, and they really shape the phenomenology, and the same terms are perturbative. Well, it's either it's perturbative or it's dominant. It doesn't look quite plausible that they are the same. And in fact, you know, phrasing it in a different way, you can also say, you say that this term is macroscopic and dominant, and it's all made by non-standard terms. But what if I can write down other non-standard terms with high derivatives and stuff, and those are also important and also dominant? And what if they cancel each other out? Because you're computing this quantity of your field, but maybe you can compute others. And how do you know they don't kill each other off? And the answer is that you don't. The answer is you don't know, because you actually only really know if you know this more fundamental theory. And you know it, and then you can make all your calculations or your computations, and so you know whether this approximation is valid or not. So you actually don't know. There's something more that we can say. So going back to the picture I showed you earlier, the question is that there is one more regime that I wasn't showing before. You've got closer to a massive source where you expect your high derivative nonlinear terms to dominate. Those are classic. You've got further away from the source where you expect the standard terms to dominate. And you've got a region where everything breaks down. You've got the region where your quantum corrections become important. And it's worthless to think in terms of the classical theory anyway. And the question is, where is this regime? Does it kick in before or after your classical theory your classical nonlinear theory has had the time to dominate? And there are two basic cases of interest. So I'm referring here to a review, a very nice review by Kurt Hinterbichler, sorry. So one first case is that of lambda-3 theories. They're called lambda-3 theories. So these are the standard Galileons. And in this case, you may expect that you've got the regimes where your classical nonlinearities dominate before your quantum correction dominate, but the standard UV completion that we have can't possibly work. By standard UV completion, I mean that the way you usually UV complete a theory is by bringing in one extra particle that takes away the pesky infinities that shouldn't be there. This is the way supersymmetry works, for instance. I'll say it another way. Normally, you start from a low energy theory, and the moment you try to extend it to high energies, it breaks down. Lots of infinities pop up that you know shouldn't be there. And often it's the case that you can bring in an extra particle, and those infinities cancel out the moment you bring it in. So it takes away all of these infinities that are not supposed to be there. This is called Wilsonian UV completion. This is the standard way of UV completing a theory, and it's the way that we know. So in this case, you can prove that you can't do this. So it may work, but we don't have a UV complete theory here, okay? So we just don't have it, we don't know. Then you've got another case, so this is called lambda 5. In this case, you can UV complete the theory in the way that we know that it works, but you've got suspicion it may actually happen that the quantum behavior is important before your classical nonlinearities are. So it may be a small cover, even you don't have the UV completion or you don't have the regime where your classical nonlinearities dominate, okay? So this is a bit of a situation. Now, we want to make a test, and this will really be the goal of this work. We want to have a theory that does have a UV completion, and we want to make this test. Let's see if the low energy theory and the high energy theory look anything like each other, and if the high energy theory as well as the low energy theory screens, which is another way of saying, let's see if this screening survives the extension to a high energy theory, or if it disappears completely the moment you extend your theory, which would suggest that the moment you have screening, you're actually outside of the regime of validity of the theory that has screening, okay? So this is the goal. One caveat that I should put in is that I said standard UV completion. So in theory, you may have that the theories can be UV completed in a completely different way that we don't know. Maybe, but then the burden of proof is on someone to produce such a theory. So at the moment, it's a bit of an act of faith. There will be some kind of UV completion that we don't know that maybe will do this, okay? Yeah.
Just one question. Is the fact that there is no UV completion, say for lambda 3, is that related to the fact that the scale of, say, RV is before quantum correction, or it's not? They're not related. It's
I don't know. I would need to look it up. I don't remember. I don't remember. It's in this review. I don't remember. I would need to look it up.
Sure.
Other questions? Okay. Yeah.
Just as a quick one, Wilsonian completion is the one everyone talks about. I actually don't have a good sense of, are there other known methods of UV completion?
So in this case, maybe you can complete the Galileon on a brain. So this is how they came to be in the beginning. So something like a 4-dimensional brain onto a 5-dimensional space. But if you ask me, is there a UV complete theory for which you can do this exercise and that we know that works and that screens? The point is really whether that UV complete theory screens. We don't know. So we currently don't have a UV complete theory that's of this kind that screens. We don't have it.
I'm asking aside from screening, forget screening. If I went upstairs to my colleagues in the
Yeah.
string theory department and said, list to me ways of finding UV completions, would they have a list that's greater than one? So I've
Yeah.
got two brain, higher dimension.
Yeah, brain, and this is the other one that comes to my mind, and then I don't know if there is, but there are not that many. So I know that there aren't that many ways that we know of that you can UV complete. There may be ways that we don't know of. As far as I know, the list is really small, as far as I know. But yeah, these are the two that I know of. Okay. Then I hope, of course, you don't go upstairs and they completely destroy everything I'm saying. Okay. Right. So this is the goal. Take a low energy theory, take a UV completion for this low energy theory, see if it screens, see if the two theories look anything like each other. Okay. If not, the screening is in trouble. Right. So this is going to be then a lambda 5 theory because we need to have a UV completion that we know, a UV completion that exists. So we're lucky. It's not like there are that many UV complete theories out there. They are difficult to spot in the wild. But fortunately, we have one. So this is Andrew Tolley and other people that produced this theory. And this is a theory of two different scalar fields. One is lighter, one is more massive, and they are coupled. One of them is also self-coupled. And essentially, this extra more massive scalar field is taking away the pesky infinitive. Okay? So this is like I described it. Is that the question?
No.
No, okay. Right.
Is this in curved spacetime?
No, Minkowski.
Just okay.
Yeah, this is Minkowski. Yeah, so it's an excellent candidate then for this test. That is screen. So let's look at what the low energy theory may look. Oh, sorry. Before that, these are the equations of motion. So this is the same theory. I'm just showing the equation of motion for this theory. Okay. So you may already see that getting an analytical understanding is not exactly trivial. So if you try to stay here and say, and just try to understand which term may dominate and when, this is actually quite difficult. So you can spend a lot of time and it's really non-trivial to understand who dominates because the theory is quite complicated, as you can see. Now let's look at the low energy theory you can derive from this. So this is it. And as you can see, you've got some quite high derivative and nonlinear operator. That's important here. And this is the theory of your extra scalar field, the one that you would think about in cosmology, essentially, okay? So this is it, the low energy theory. And in order for this theory to make sense, it relies on these operators, on this series of operators that I'm showing here, to converge. So if the series converge, then the perturbative approach is correct, and then everything is fine. If this series doesn't converge, you are already outside of a perturbative regime. And I mean, in principle, you can work with any theory you like, God given, but then it means you're in trouble. It means this theory doesn't really make sense for the point of view of making predictions, okay? Now, you may already notice that if you want to make these tests, like see whether these theories look at each other, whether they make sense, you've got quite some horrible operators to deal with, okay? So those that do any computation know this is nasty, okay?
Sorry, I'm not really familiar with EFTs. How do you obtain the low energy theory?
Okay, yeah, that's a good question, actually. So, and I've already put an asterisk here, okay? You can do this by substituting this equation of motion into the other one.
Okay.
Okay, so you sort of solve for the more massive scalar field in this case, and you put it into the other equation of motion. Now, this is where the asterisk comes in. This is not, strictly speaking, correct. So the reason why this is done is this is the way you would do it in cosmology in some sense, by not checking whether the perturbative approach is correct in the first place. But if you assume it's correct, then this is fine. The correct way of doing this would be to start from the Lagrangian and integrating out at this level. If the perturbative approach is correct, you're fine in both ways. If it isn't, this is not likely to be correct. But when people talk about integrating out, they actually very often mean this. They just mean substituting at this level, and this is not exactly the same as integrating out the heavier field, even though this is what people mean often, okay? But this is how this is done in this case. So you substitute the one equation of motion into the other, and so this is how you come up with these operators. I'm a bit spoiling myself here by saying this is not exactly how you should do this, but yeah, let's pretend I didn't say that.
And pi is some combination of the two scalar fields?
No, I just call it pi because I want to hide that. I want to highlight that it's a low energy theory. So I'm simply, yeah, you're right. I should have said. I'm simply using the term pi to say this is how I'm going to call my low energy Galilean field in this theory. It's a so. Yeah, so this is a light scalar field. So you may already ask, is it a combination or not, blah, blah. In this case, so if you make the calculation, blah, blah, this is the light field here.
Okay, so it's basically pi on the previous one.
Yes.
Is alpha dimension?
No, actually, it depends how you define it. No, I don't think so. We need to check it. No, I don't think so. Yeah. Okay. Great. Right, so this is the goal. Let's compute the scalar force for the high energy theory and for the low energy theory. Let's see if any of them display screening, but let's also see if they look anything like each other. And let's see if the perturbative approach was correct in the first place. Okay, so we can do it because we've got this very nice test bed, this UV complete theory. Right. So we have a problem. This is one problem we often have in physics, the difference between the spherical cow and the real world. So if any of you does simulation, you will know that derivatives are bad, second derivatives are bad, bad, and higher derivatives are bad, 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 bad. So derivatives are nasty. And in this case, you've got horrible operators, and you get up to a fourth derivative, and you've got a second derivative of something to, of another second derivative to some power. It's horrible, okay? So if you try to compute this the normal way, yeah, it doesn't work. Right, so you need something clever. And for this, I will use the finite element method. So this is a method that I love. I really like it, and I'm going to advertise it with much passion for this reason. It's actually really good for this case because of you've got these high derivatives and you can lower them, okay? Okay, so now I'm going to give you some information about this method. This is going to be a little bit technical, but A, it's very beautiful, B, it's short, so please bear with me. Before I go there, questions? No, okay. It can be used for lots of things, by the way. It's used in structural engineering. It's quite nice. You can use it for your projects as well. I really love it. Yeah. Okay. So essentially, it comes down to solving on a computer something that's continuous using something that's finite. You need to do this in such a way that by solving that which is finite, you will get a good approximation to that which is continuous, an accurate approximation of that. So we've built our code. It's called Phyenics. It's publicly available. It's called Phyenics because it's built on a Phyenics library. And in my intentions, I've written it in such a way that hopefully anybody can use it and modify it for their own purposes. Whether I succeeded or not, you tell me. But that was the intention there. That was the way in which I tried to write it down. And it essentially does everything that's needed for this purpose. Now, how does the finite element work in a nutshell? The first step is to discretize your domain, the domain on which your field profiles and other things live. One key advantage of the finite element method is that you don't need your discretization to be uniform. So typically, in the way we do things, we take a uniform discretization. In case we split some of the cells, you go on to do, for instance, adaptive mesh refinement. You split them and make splits of splits. But in this case, your cells can be as crazy as you like. So this is why it's also very useful in structural engineering. You can have very complex shapes. In this case, because they wanted to really show off, they carved the shape of a dolphin inside a mesh, okay? Now, what do you do then? You discretize not just the domain, but the function space. So this means that on each of these cells, so in this case, they're triangles. You don't need them to be triangles. Let's just take this example for the moment. On each of these triangles, you define a discrete finite dimensional function space for that cell. And then you do this for all the cells, and then you stitch them together according to some prescription. And you obtain a finite dimensional discretized function space on the whole domain. One example in which you can do this is not the only way, but one example is by using Lagrange polynomials of some order on each of these cells. And then you can stitch these function spaces together in such a way that your function is continuous piecewise or also discontinuous piecewise, depending on what you need. For the profiles, you will want it to be continuous because it's what physically makes sense. Okay. For the derivatives, you may want it to be discontinuous for mathematical reasons I will not go into right now. But for the profile, you want it to be continuous. Okay. So tiny function space on each of these cells, and you stitch them together. Okay. Yeah.
I noticed you've said basis polynomial. So are you saying that basically you can describe what would normally be a continuous function on this domain space using these basis functions weighted appropriately? Is that kind of what you're doing here?
Yes. Yes. You just need it. So what you needed to do is to be an accurate approximation. So you need to have good. So it will be a set of things. The discretization of the domain, the discretization of this function space, a number of things that together give you a solution that passes some test. So This is really what you obtain. So for instance, if you take basis polynomials of degree 1, we can't compute derivatives of order 4. They're going to be identically 0. Mm-hmm. So this one example, that would be a bad discretization that wouldn't work. You need to have some, and you need to make tests. I mean, it's difficult to know it in advance. You often make some tests to see that the solution you found basically satisfies some tests, meets some criteria, and you think it's the accurate solution.
Okay, right, thanks.
So basically, you may miss things, but not important ones.
I see.
Okay.
Is this like a multidimensional spline?
Is this a multidimensional spline? Part of it. I would say. Okay, so I think it's more than a spline because it's important for what I will discuss. It's important that it's a vector space, that the function space you write down is a vector space. So, so you're not just joining the dot, you must join the dot in such a way that you can talk about basis functions and you can have a vector space structure. I'm going to show you why in a second. Right. Next step, let's go back to the equation you need to solve, okay? So I'm going to show it for the Poisson equation because it's simplest, but of course you can do this for other equations. So standard gravity, Poisson equation, you've got your system of equations. It's typically one differential equation and boundary conditions. They're called Dirichlet when you're defining, when you're requiring that your function has some value in some parts of the domain. They're called Neumann when you ask that the derivative of the function has some value in some part of the domain. This is a general problem you have. In our case, the boundary conditions are a bit annoying, they're a bit hard, because what you can say is that your field has to be 0 at infinity, and the derivative of the field, the gradient, has to be 0 at the origin. So you want it to be smooth at the origin, otherwise your origin would be a special place in the universe, whereas it's just one point in which you're centering your frame. So you don't want it to be a special place. So you have a Neumann boundary condition at the origin and one Dirichlet boundary condition at infinity. This is already annoying, okay? So you have to make sure this is satisfied. This is another reason why the finite element method is good for this. I will say why in a minute, okay? Now, the next step is to bring in the weak formulation of that equation. So instead of asking that your equation holds in an absolute sense everywhere, you ask that it holds with respect to a set of test functions that you choose. So you define your space of test functions. You say, I like these test functions. I need the scalar product of both terms of my equation with respect to all of the test functions to give an equation that holds. So this is a weak condition. This is why it's called a weak formulation. But it's not so weak in the sense that you need this to hold for all of the test functions, and test functions must be in a vector space. Now, in our case, we use the Euclidean scalar product because it works for us. So in order to compare with the analytics in the specific subregimes in which they can be obtained, we restrict to study spherically symmetric cases. So one of the tests that we make is that in the case where we can't derive some analytics at all, we want to recover them. So we restrict to study spherically symmetric for this reason, and so we use the Euclidean scalar product for this. Now, watch what happens to the Neumann boundary conditions. This is one of the reasons why the finite element method is good for this. You start from a Laplacian, but you can integrate by parts. And by integrating by parts, you're lowering the order of the derivative and you're bringing in the Neumann boundary condition. So your original system is written with the Neumann boundary condition in place naturally. So normally you need to enforce the boundary conditions. In this case, that happens naturally. Quite cool. And this is why you need the structure of a vector space. Coming back to your question, let's see what actually has happened. So we end up with, so our Poisson equation has been turned into a product of gradients, Neumann boundary condition, and your original source term. Looking closely, you can see you end up having a bilinear form of the solution you are after and one test function, and one linear form of your test function. Why is this cool? Because if you have a structure of a vector space, then it turns out the moment so if you remember from your linear algebra, the moment you've got a bilinear or a linear form, the moment they're defined on a basis, they're defined everywhere. Because the bilinear and the linear form preserve the structure of vector space. They're really nice and very, very well compatible with the structure of vector space. So we have this bilinear and linear form, which for simplicity now I'm going to call A and L, but they are those integrals that I showed you. Now, I said that we decompose functions in terms of a basis functions and some coefficients. So I would use this vector space structure. Then I impose bilinearity and linearity. And look what happens. The moment I define on basis functions, they're defined everywhere. Your complicated Poisson equation just becomes an algebraic equation for your coefficients. So what you end up solving for is just the coefficients of your expansion. And this is just matrix times vector equals vector. This is a normal algebraic system of the kind you solve in high school, okay? So you start from a partial differential equation, hard, horrible, difficult. You end up with an algebraic system. This is why I think it's so cool. Okay, I didn't invent the finite element method, obviously. This is the credit to many other people, but I think it's so beautiful, okay? Right, before I go on, questions?
Just to clarify what
Yeah.
you're solving for in your matrix sense of the coefficients of U,
Yeah.
which are your A's, which are in that matrix. Is A a matrix or
Yes, so this is your bilinear form that corresponds to an A matrix. In fact, can I have a pen? Maybe not. Okay.
Ashim, there's one behind you.
Okay. This one more. Yeah. So you've got your solution. Okay, you can expand it in terms. Yeah, I'm sorry that the remote people will not see. You can expand it in terms of some coefficients and some basis functions. Okay. Now let's put that into a bilinear form. So we've got a bilinear form of your solution and of the test functions. We've got
very faint, I'm afraid, Daniela, is there?
Someone goes up.
That's better.
Did you find one?
yeah.
You were pushing harder with that one.
Oops, sorry. Yeah, right. So in this case, I'm just going to write an EJ because so this is the test function. If I ask that the equation holds for all the basis test functions, then it holds for all test functions. Okay, so this is one basis factor of the test vector space. This is one basis factor of it's called the trial vector space, the one that want to describe your function, the function after. Okay, now this is bilinear by definition. Then this becomes your bilinear form evaluated on basis vectors, and this is by definition a matrix. Okay, and then I can also make a U vector with the UJ. Okay, so UI, sorry. Okay, and then so same with the linear form. Okay, so your linear form again, same thing. It's just the test function, so I can just restrict to basis test functions. So then this L evaluated on the basis test functions is a vector. Okay, and then this is why you end up having matrix times vector equals vector, and the vector you're solving for is the vectors of the coefficients of your function according to that basis function. Of course, because you are choosing the basis expansion, you need to check that all of this in the end is making sense, that you're solving for what you want to solve, and you're not getting some discrete solution that is not an approximation of your actual solution. Yeah.
How do we know that the set of basis vectors is finite dimensional?
Well, but you make it by definition, because so let's take the example. So as I said, you can make other cases, but let's take the example of Lagrange polynomials of some order onto a discretized domain. The domain is finite. The number of cells is finite. Okay, so you will have, let's imagine you've got 1,000 cells. Okay, I'm putting in a number. Then let's imagine you've got degree 2 Lagrange polynomials on each of these cells. Then the moment you stitch them together, you've got a finite dimensional vector space. Now, the number of basis factors you have in the whole thing will depend on your prescription for stitching together. If you ask that they are continuous, then you've got less freedom because they ask that these functions must have the same values on the boundaries they share, so then the freedom is less. If you allow them to be discontinuous, they've got more freedom. So that depends on how you choose to stitch them together, but they're finite by construction.
Okay. Yeah.
Other questions? Okay, so then the extra bit is that though that was a linear equation, instead we have a highly nonlinear equation. So this is simply solved by using some nonlinear method of your choosing. So this you're probably very familiar with. We use the Newton method. We could have used other methods. So it's just some iterative technique in which you essentially have some giant root finding exercise. So instead of trying to find one number, you need to solve for all your degrees of freedom in the function. So it's just some giant root finding exercise where you try to solve some nonlinear equation of all these degrees of freedom iteratively. Okay, you start from some initial guess that you believe is good enough, and you iterate until you find some final guess that respects some requirements of tolerance. Okay. Okay. Right. So this concludes this short review of this method. Now, before I give you the results, before we talk about UV completeness again, which is actually what you care about, I'm going to make some advertisements. So I'm going to show you why this was a good thing to do. So this is a movie, so movies, people like movies usually. What I'm showing you here is a case of what's deliberately difficult. So whenever you've got the scales that sort of collapse together, this is usually more difficult because you've got some degeneracy. You need to make sure you're solving them all together. So in this case, we've got that the quantum wavelength of the light scalar field, where the quantum wavelength is the length over which you can expect your scalar field to interact, is just 10 times larger than the source radius. You've got that the quantum wavelength of the more massive scalar field is just 10 times smaller than your source radius. So this is all hard, okay? So we can expect it to be hard. This is why it's a good test bed. What I'm showing you here is what happens when you've got a source profile that is a smooth top hat profile, so it has a transition, and I'm making that transition more or less steep. So this is the source profile, okay? Now, because the heavy field has a quantum wavelength that's smaller than the source radius, you can expect that modes in your heavy field will be excited by this transition. And in fact, they do. So this is not new physics. This is something you can expect. But to be clear, in order to solve this accurately, I need to have a box that was 1 billion times the source radius, and yet I can solve for these tiny features just around the source radius. And the reason why this works is precisely because I can put the points where they're needed. I don't have to put like so many points further away from the source. I can just put the points where I really need them, okay? So this is why it works. And as I said, these features are expected, but try to do that analytically. Try to get this. You just know that something is going to be excited. It's difficult to describe, you know, analytically to have such a good understanding. Then some other aspect is, like I was saying, you look at the equations, they're horrible. It's quite difficult to know what's going on and who is dominating. But instead, things work. So you can actually look at all the regimes you can have. So this is what to expect for the terms in the two equations of motion, the one for the light scalar field, the one for the heavy field. And as you can see, you can have different regimes in which different terms come to dominate. So it's actually, you know, you can reconstruct them in a way that makes sense. If analytically you couldn't. And finally, this is the bit that I'm most proud of. So solving for the scalar field was relatively easy. Solving for the operators was hard. What I'm showing you here is the reconstructed Laplacian of a Laplacian to the power of 7. This is horrible numerically. And we can solve this accurately, recovering all of these regimes. So the regimes where the light field dominates, and for those we can make some pretty good analytic prediction, except that of course you don't know if they match, and you have to put in by hand some constants because you can't predict. But we can recover also this tiny little bit here, where it's the only bit where your heavy field dominates, and you can recover this tiny feature that correspond to that case where the tiny feature are excited at source vacuum transition. And you can recover all of these regimes. And to be honest with you, when I started this, I didn't think we would get to this case, but it worked. So I'm advertising it. Okay, so it's quite cool. We can solve for these horrible things. Okay. And now we go to the big answer. So Vainshtein screening and UV completion. What do we see? Is the perturbative approach correct? And does the UV theory screen? And all the rest we've been saying. Before I go there, questions? Yeah.
Very basic one. In the previous slide, you called the term at the top, right? You called that an operator, but it's being evaluated on phi, I assume?
Yeah, phi is a function.
Right. So is this a term or an operator? I'm just getting confused by the use of operator here. So,
right.
Yeah.
Yes. So okay. So I'll go back. So I think it's this slide. So the first order operator is in the equation for the in the IR theory equation of motion. So if you write down the IR theory, the first order operator is here. That I was showing was the third order operator.
Right.
So in order for this to make sense, you need the tower of operators to converge.
Mm-hmm.
Okay. So it is or it isn't in your equation, depending on where you truncate your equation.
Right.
Okay, so the first order is in this equation, then you will need to have all these other operators, but you choose to ignore them.
And the slide you were showing there was the evaluation of that operator on the field phi.
On the solution we recover. So
Right, right.
we recover the solution phi for that
Mhm.
system, for those parameters, and we evaluate the operator on our
the-
solution.
okay, okay,
Yeah.
sure,
yeah.
okay, thanks.
Other questions? Okay. So results. Does it screen or not? The two theories look nothing like each other. So here I'm showing you the ratio of the scalar force to the Newton force for the IR theory and for the UV concrete theory. The IR theory is displaying quite strong screening. So you can get a reduction of strength for this particular model up to 10 to the 8 compared to the Newton force, starting at some Vainshtein radius, except that the UV theory doesn't at all. The UV theory doesn't screen at all. The two theories look nothing like each other, and the Vainshtein radius is simultaneously the radius at which your nonlinearities become important, and so you start screening, and the radius at which your theory breaks down completely. Okay, so let's see this in terms of the operators. I was saying, if your series of operator converges, everything is good. Otherwise, you're in trouble. So this is four order of operators. The first order is less important than the second, which is less important than the third, which is less important than the fourth. Your series doesn't converge. This doesn't necessarily mean that your series diverges. It just means that your perturbative approach has completely broken down. Okay, so the series of operators doesn't converge. The perturbative approach is not appropriate. You can't speak of Vainshtein screening because when you talk about Vainshtein screening, is outside of the regimes of validity for your theory. Okay, so summary and conclusion. Vainshtein screening is quite effective in theory at high inductive force in high density regimes. And the problem is that it's characterized by equations which are quite horrible. It's one of the reasons why it's difficult to test. We developed a code, the finite element code, that was able to solve for these equations with horrible operators. And we used it to compare a theory of massive Galileons against one potential UV completion. And we showed that the two theories look nothing like each other, and that the theory that screens does so outside of its regime of validity. And essentially, this means that it's unclear that Vainshtein screening can be invoked within the limits of validity of the theories that use it. The caveat is that we can't exclude that there is going to be one day one UV complete theory for the other set of theories that works and that screens. So we can't prove that there exists no such a theory. But in some sense, you could argue that the burden of proof is on the other side. So for the one case that we could test, it didn't work. In some sense, you're asking an act of faith that such a UV complete theory exists, but we don't have it. So you could argue that the burden of proof is the other way around. And with this, I conclude.